Okay, thanks Yeka for the introduction. And today I basically want to discuss the paper of Christodoulin 91 about this nonlinear nature of gravitations and gravitational wave experiment. So let me start by set up my null infinity. We have seen this many times during this summer course, but in this setup I want to connect it to a Cauchy initial data set from spatial infinity within the framework of the stability proof of Christodoulin and Kahneman to have a precise decay rate of the various curvature component, and this will be important later on for the study of the memory effect. Okay, then as we already see a little bit from last time, we will first there will be a precise decay rate for the curvature, biocurvature tensor of everything. All the space-time discussed today will be vacuum, so we are interested in particular the biocurvature tensor, and we'll see that the largest or the component which decay the slowest is this alpha bar that we have seen before, and through the Jacobi equation, we want to establish that this will be responsible for the accelerations in a gravitational wave experiment. Okay, so once from here, we will sort of accept this fact and sort of cut it off from wave experiment. We'll study quantities relating to this using the null structure equation that Henry stated in his talks. Well, all except one Ricci equation that I have to also mention. Okay, then using these precise structure of null infinity and null structure equation, we want to study the relations between various geometric quantities using the null structure equation and taking limit toward null infinity. And this will be the memory effect. And since this is the acceleration, other quantity will be velocity and displacement. And the displacement is what, the permanent displacement is what this memory effect is. Okay? We will be more precise later on after we state the various notations. Okay, let me first, just to set up my notation, write down the following picture that we have seen many, many times throughout the course. Right, we have a surface which denoted by x. Sigma will be used for something else in this result. So let me write my surface x. Okay, I have a pair of null directions L and L bar. Okay, so this will be null normal oriented as depicted in this picture, both future directed and one going L going outward, L bar going inward, and normalize so that this is -2. Okay. And first of all, we have the second fundamental forms in these two directions as well as the connection forms. Okay. So let me write them down again just to fix my notation. Second fundamental form in the direction of L. Chi bar is the second fundamental form in the direction of L bar. And the connection form of the normal bundle right here, x and y's are tangent vectors to x. These two are symmetric two tensors, and of course let me denote by gamma ij the induced metric. Again, small sigma will be used for one of the curvature component as well, so let me not use that for the induced metric. Okay, and with the metric And the second bound form, I can decompose second bound form into trace and traceless part. Okay? So, and we have seen this before, so let me just I did as a 1/2 times the trace of the metric plus the traceless part. Okay. I can also decompose, well, since I'm in vacuum space-time, the Weyl curvature tensor with respect to the friend adapted to this now friend L and L bar. Right, so this will give me the 10 independent component of the Weyl curvature tensor. It will start sort of distant then in the order of decay rate in R later on. Okay, so alpha bar, I plug in 2L bar into my Weyl curvature and then I put it in X and Y. This will be symmetric traceless 2 tensor on my surface. I have a 1 form beta bar. Put in X and then L bar, L. Okay. Then there are 2 scalars. Rho, which is 1/4. L bar. Then there's another scalar. Delta, which is I plug in the same vectors but into the Hodge dual of the Weyl curvature tensor. This is just so that I can keep the 1/the constant. Otherwise, I can also find the volume form epsilon xy on the surface and write this as one half of Weyl curvature tensor value at x, y, L bar, L. This is antisymmetric in S and Y, but this will make the coefficient more symmetric. Okay. Then finally, I have 4 more components: beta and alpha. Both are carry 2 independent. So basically, you exchange L and L bar. Okay, so these are my curvature component. Again, I've seen them before. Just set out the correct coefficients with respect to the friend I'm using. Okay. Again, this notation follow is in line with the notation of Christopher in his paper. Okay. Now we want to connect spatial infinity to null infinity by the global stability result of the of Christopher-Kleinemann. Okay. So that may be somewhat vague about the condition, but I will be precise about the curvature decay rate at null infinity. Okay. So again, suppose I have a initial data set satisfying the vacuum constraint equations of vacuum initial data set, which is strongly asymptotically flat. Okay. And be precise, this means that the metric, well, I think it's probably asymptotically Schwarzschild. It's probably the more. The Schwarzschild metric plus something which is small of r to the minus 3/2 with 4 derivatives, each decay 1 order faster. And k is small o with 3 derivatives of r to the minus 3/2, and which is, well, this is precise, but the next one will be sufficiently close to the trivial data in Minkowski. Sorry, and I should rewrite this as R3. I want to fix the topology as well.
It's still to the fourth power.
This one's three derivatives.
Still you want to conformal to Schwarzschild.
Right.
Is there still fourth power?
This one?
No, the conformal factor, 1 plus 2 is
Well, m over 2r to the power 4 is the same. They're squeezing the lower order term. I'm allowing r to the minus 3/2 small of that, so sufficiently close to the trivial data, and I will not be, you take a full course to write down the suitable conditions. Then the conclusion is that the global development gives you a smooth space-time which converts back to Minkowski. So a global is a smooth global development which is asymptotically flat in the space-time sense. Okay. The maximum development, right, the largest unique solutions to an Einstein equation. Smooth, globally asymptotic space-time. Again, this is somewhat vague, but everything, you have a space smooth development which converges to Schwarzschild, but the important part is the decay condition I'm going to state below. Okay, so I have, in particular, as part of the proof, they construct the following 2 global coordinates.
not really global.
Well, I think in their case it's global because every time you have to transfer the coordinate backward through the optimal structure equations all the way back to the final size, limiting size, yeah, right, right. I guess in the region which is sufficiently far away. Ut, and it's near the null infinity, so that u equals to constant is a null cone, and in the proof t equals constant is a maximum space-like hypersurface. This is not particularly important, but what we'll use is the decay conditions on the on this curvature component. What's that? On surface with constant t and u, I have the following decay rate. Okay, so here r is the area radius on the surface. And tau minus is root of 1 plus u squared. Okay, so alpha bar is the largest component in R, so decay at the rate r to the minus 1. But we'll see that we will trade off decay rate in R to decay rate in essentially U. Okay, so beta bar. I have faster decay in R, but slower decay in. Sorry, this is tau. Sorry. I guess there's a tau lower minus, but I don't really need the tau plus, so let me just write tau. Right. And really for large U, you can think of just tau is the same as absolute value of U. I'm going to use that anyway. And these four are big O's. The next two are small O. Okay, so I guess I could probably reverse this too. You are sort of losing, getting powers in R, but losing powers in U. The last two is fairly small that you don't really use them, so we don't really need to track their powers in U. Okay. Okay, so of course this is the proof use which small data, which is sufficiently close to the to this. We will assume that we don't necessarily start with a small initial data, but nevertheless we'll assume that our space-time has a null infinity where this quantity satisfies the same decay condition, which potentially results from large initial data sets such as a black hole merger. Again, whether you can assume that, not clear, but at least we can work within this framework to get something interesting. So, have decay rate and
Do we roughly know, like, U is equal to T minus R?
I think the construction should also give you that. Right. Minus infinity. You can go to minus infinity, right? Right. So you can go to minus infinity will go back to the initial data, or at least in the diagram. Okay.
But this is true. But this coordinate still rely on this square more size, right? So you still require T to be large enough.
Again, I think every time you have to really travel backward. So at least near null infinity, you can travel backward, solving a wave equation. I mean, how much you can go inside is something else, but at least near null infinity, one can really travel backward. And you have to travel backward to adjust your initial foliations and so on and so forth. Okay, so the next step, the notation is slightly tedious. Basically, what we want to do is we want to find, well, these have this decay rate. We want to rescale them, for example, multiply this by R, and then take the limit. But in order to do that, I have to be a little bit more precise about how I identify my coordinates at near null infinity. Okay? So let me fix a null cone, and without loss of generality, let me say this is U equals to 0. So I fix a outgoing null cone. And also let me fix this is generated by the geodesic, L is the L generate the geodesic on this null cone. Null cone C goes to the set and on C. So again, this is not perfectly important, but okay. So I have from L, I have the affine parameters, and let me look at the level set for the affine parameter, and let me take one level set, which I will call sigma 0. This is a level set of the affine parameter. Later on, we will do this for each level set. Okay.
You don't forget about T, right?
right. Okay, and I have, in fact, even U will be forget very shortly. They will construct a new U. I have L here. Okay, then I normalize L bar. Once I have L on x0, I can find L bar according to the same normalization. Okay. Once I have L bar, I can now travel in the inward, I can generate the inward null cone by extending L bar by extending as a null geodesic. To generate a inward null cone. By C bar. Okay, so eventually I will take quantity look at the structure equation on this inward null cone. So on this inward null cone, L bar is the geodesic, generated geodesic. Okay. So in a way, this is actually closer to the picture Henry discussed before. The inward null cone is the one with the geodesic. So when we change, right. Okay, and again, I will fix a coordinate starting on x0 and essentially drag then first through L using the drag and then drag then through L bar using the drag to have coordinate on each of the level set of the offline parameter. Okay. But let me do this following Cristolo's notation. This essentially is this. So I take an abstract S2. I have a diffeomorphism from S2 to X0. And I'm first going to drag the coordinate along L. So I have a family of this into C. I'm requiring that the trajectory of a point is the null geodesic generated by L. Curve, geodesic, generated by L. Okay, so I have a family of embeddings into the affine set of constant affine parameters on sigma 0. Okay, then for the affine parameters, which lies in here, again, I'm using R as the area radius. I'm setting U on C bar to be the following. Again, so this U is no longer the same as that optical function generated by, to be R minus twice of R0 minus R. Okay, so it's proportional. There's a one-to-one correspondence between the affine parameter set, but not the same. And then I find sigma U from x2 into the surface of constant U such that this generate the this is the diffeomorphism generated by L bar. Okay, and this is essentially as in Lucid, this is you start with a fixed coordinate on x0, drag using L along C, then drag using L bar along the inward null cone. But, right. Again, this U is no longer the same as that U. Right. Okay, so using this, I can then pull back things on XU using the pullback of phi U star. Okay?
But R is the same R.
R is array radius, so assuming you have the same surface, it's going to be the same R. R always stands for array radius. Even if you change your surface, then on your new foliation, R is still the array radius in that foliation. Okay, so now I can use this to pull back quantity onto x squared, onto the fixed surface x2, and evaluate the limit. Right, for example, if I pull back if we scale the metric by r to the minus 2, pull it back, I will have the limit will be a metric with constant curvature. Okay, and this will denote by sigma 0. Okay, and if I write covariant derivative with respect to 0, will be the covariant derivative with respect to the sigma 0, evaluated on x2 after I pull everything back to x2. Okay, and so then I have the Christoffel symbol with respect to the original induced metric. Okay. Okay, so now with this, I can evaluate the rescaled limit of these quantities. Again, when this is written down, this is about its length. So these are the values when I put in a orthonormal frame. Now I'm putting in the frame which has length r. So when I take limit, the powers of r will be slightly different depending on how many vectors I put in there, okay? But let me write down the limit of the quantities, okay? So again, this agree with, I'm just taking the rescale limit of, the equation that I just erased. For example, alpha bar has order 1 over r, but it's a 2 tensor, so if I evaluate on this coordinate frame, it's going to be 1 over r times r squared, so it's going to be of order r in the frame we're talking about, so I divide by 1 over r, take limit, and the limit is called a, okay? B will be the limit of the leading order term of beta bar, which is called b. And rho and sigma, the limits are p and q. Okay, and the other two component of the curvature decay sufficiently fast that I don't really need them. Okay. I can also pull back the 2-second fundamental form. To be the two, give me two family of traceless symmetric two tensors on X2. Okay, and again, of these are, well, traceless symmetric two tensor vectors, function, traceless symmetric two tensors on X2, which depend on the parameter U. Okay. Okay, so alpha A is really the leading order term of alpha bar. B is the leading order term of beta bar, and so on and so forth. Okay, so sorry for the heavy notation. But first of all, why does alpha bar, or in this case A, tell me about the accelerations in gravitational wave experiment? I can erase this. Now that I have all the limit. I suppose I have two black holes merging in the middle, and they are sending out signals toward non-infinity. Right? I'm doing a gravitational wave experiment here, and what I can measure in this case is I take two particles, connecting them by laser beams to measure their distance, right? And as the gravitational wave passes through the particles, I'm recording the distance between these 2 points. Okay, so I cannot really draw this well at non-infinity. So let me draw it as if the signal coming from more like a inward from here, although we should know that the information travel along null direction, but I cannot really draw, well, I can draw to geodesic, but it's, right, so suppose some information is coming in from here. I'm measuring the distance between two nearby points here. Right, so I'm taking geodesic in t directions, and again I have a, right, so this is the point where I have to come back to having a t foliation. So I measure the distance in a different t slices. I'm tracking the distance between the 2 points. Okay, and they're nearby. So essentially, I can just look at the Jacobi field equation, which tell me geodesic deviation. Because it's asymptotically flat, so how much their coordinate deviate just tell me what's their distance. Right, so and the Jacobi field equation will be like this. Right, so this is something essentially we know, right? While curvature gives us the accelerations of geodesic. Okay, but in this case, because of the decay rate, this is the single largest component. So if I want to look at the leading component of the geodesic deviation, it has to be coming from A. All the other quantity will be 1 over r squared or lower. Right? And really, I will achieve this acceleration if I sort of put my sensors perpendicular to the direction where the wave is coming in. Right? So I'm really putting, on the coordinate sphere, I'm really putting my 2 points to be perpendicular to the direction. Then this direction will be a EA direction. Right? So here I'm really putting AB here, and T is roughly 1/2 L plus L bar over 2. Right? So if I look at the component here, the largest one will be L bar, AB, and the rest will be of lower order. So if I start in a position like this, then to error of 1 over r squared, these 2 points going to stay on the coordinate spheres, but their distance will change by r of A of the direction join these 2 particles. Okay. So this gives me the acceleration. So I really think of A as the acceleration in the gravitational wave experiment. Okay. Okay. Now, from here on, we come back to math. So, of course, this is the note that these quantities, they are not independent of each other. We have Gauss equation, we have Kodasi equation, and other propagator equations which tell us how they change according to each other. Right, so these are referred to as now structure equation. And just to simplify the equation, I think in Christo's work is writing d bar as the d derivative along the direction of L bar. But to agree with Henry's notation, that's essentially ddx. So I would just write ddx of the quantity instead of d bar of something in the propagator equations. Okay. But let me start with the Gauss-Kodasi equation. The Gauss equation, again, this applies to any surface with the null decomposition. K plus 1 over 4 trace chi bar plus 1/2 trace bar minus rho. Again, as because of the orientation, I think in Henry's talk, this would be minus, but the L bar is in the reverse direction. And then I have the Kodasi equation. So it tell the divergence of the two second fundamental form. Connection form put into the so this divergence, this is an equation of one form. Right, so this is, I contract the connection form into the second form, I get a one form as a result. Beta bar. The beta, okay. There's one equation that was not in Henry's talk. It's the Ricci equation, which tell me the curl of the connection form. Okay. Then I have equations which tell me how this quantity changes along the inward null cone. Okay. And the first one is the Richard-Dooley equation. Okay, and I think this is formally not written down in Henry's talk, but you have the propagator equation for sigma bar, so it's not difficult to find the evolution of its traceless part. And let me just write down the result. In fact, not difficult. Okay. There's a derivative of the connection form. And then I have derivative of trace chi and trace chi hat. and a for me to be lazy plus all the terms in R. This is really, really long, but this is the only term of order. I mean, this is of order R to the minus 2. And this is the only term of order R to the minus 2 on the right-hand side. And this is the only term I'm going to use, so I'm not going to write the other 10 terms, which is of R to the minus 3 or lower. Okay? So, what can we use this to tell us about the geometric quantities? And in particular, we'll be interested in A, sigma, and C, because they, again, the leading order term of alpha bar and the two second fundamental form. Okay? So the first lemma will tell me that they form a system of linear ODEs, and which means that we should really treat the other two as velocity and displacement. Okay? So this is the first lemma we can derive out of the structure equation. Remember, this is the leading order term of alpha bar that we should think of as the accelerations in gravitational wave experiment. I'm saying that the derivative of the leading order term of chi bar in U equals to this. I should really think of this one. I should think this as the velocity, and then the derivative of sigma equals to the velocity, so sigma should be considered as displacement. Okay? And this is fairly straightforward from these equations, and in fact, I'm going to just use, well, this and this. Okay? If I multiply this equation by R and take limit, or right, multiply this by R and take limit under phi u star, then this is of lower order. This pull back to this, and alpha bar the limit pull back to this. The 2 comes from the fact that ddx is twice of du. Okay? Because you're setting out your coordinates so that L plus L bar 1/2 is ddu, and the L direction, the derivative gives you lower order terms. So ddx is really twice of du. Again, a little bit of counterintuitive. So this is that. And the other one, you multiply this equation by R squared. Again, the lower order term disappears when you do that. And you have R squared. There's a 2 over R here. Then that absorbs 1 power of R. The other power of R goes to here to give you this. Okay? So from the 2 propagator equations of the traceless part of the second fundamental form, I can quickly derive this. Okay? So again, we already established that A should be the acceleration. So this should be the velocity, and this should be the displacement. Okay? So far, this quantity look linear, depending on each other. The next theorem, which is sort of the nonlinear part, is that in fact, this is sort of a infinitesimal displacement. But if I look at the displacement from minus infinity to infinity, the permanent displacement, then instead of this sort of linear relation, I will actually see a quadratic relations. So in a way, there's something you remember from the Okay, so first part of, well, I want to say this is the displacement. So if I want to talk about permanent displacement from minus infinity to infinity, well, first I should make sure that I can take those to limit. And so this is, the first part is the following. I want to establish that this, the term, again, now it's defined on R cross X2, but the decay rate in U, when U goes to positive infinity, is of order U to minus 3/2. And in particular, once I have this, then it's fairly easy to establish that this to limit this limit exists. Okay, so I can talk about permanent displacement. I can take limit of sigma from U to negative U. And the last one is really the main part. Tell me that I want to determine this difference. Well, it's a symmetric trace, these two tensor. So it's determined by its on X2. So it's determined by its divergence on X2. In fact, its divergence it's a gradient vector field. We should have. Sorry, I'm packing too much information into this one line. I should define separately. So from here, not only can I define these two limits exist, I can also define the following function on X2, which is the integral of norm square of this from minus infinity to infinity. Okay, again, because of this rate, this function exists. This integral converge. Okay? And Laplace of this potential essentially is F minus its average. Okay? So because of the mass loss formula, I should think this as the gravitational energy radiated away in a given direction. So after subtracting its average, I found the potential for that, and its gradient vector field give me the displacement. Okay? And among other things, I mean, these relations are linear, but here F more or less depend quadratically on the, well, depending quadratically on this, which is of the interesting part. But also, yes? Yes. Yes, we will show that. Yes. Okay. Well, it's from the structure equations, which we'll see very soon. Okay. So these are the main statements we're going to prove. Well, really the last one, but the previous one sort of prepare you for it, telling you that you can find the limit, really find the displacement, and it's given by its Hodge decomposition in this way. Okay. So, how do we establish this? Actually, beforehand, let me write down two more other quantities. I know that trace chi decays like 2 over r, so h indicates its next order term. Again, I could probably use phi u star to write it more rigorously, but just write it this way. I multiply trace chi by r squared, subtract the leading order term, so that's this give me the next order term. Okay, and also I have the modified, well, I have the following bar. Bar is k plus 1 over 4 trace chi bar plus divergence of the connection form. Again, the integral of this will give me Hawking mass after multiplying by r. So I'm adding a divergence term. But in bounded coordinate, this will, if you have bounded coordinate, then this will be the modified mass that we have seen to this point. Okay. So let's look at the structural equations. So first, let's start with the two Kodazzi equation, right? Sigma and because they are traceless symmetry 2 tensor. So again, they will be determined by its divergence. And since we're interested in determining these quantities, we should start with these equations. Okay? We multiply, of course, these two equations have slightly different order. This I should multiply by r to anchor the leading order term. If I just multiply by r, I'm going to get the beta from here. Okay, so I'm going to have divergence of this equals to b. And I multiply the second equation by r squared. Take limit. Divergence of this is 1/2. From here, I will pick up h, because the 2 over r is constant, but I multiply by 1 more by r squared, so I have to pick up gradient h plus r squared times beta, so the limit is going to be z. Sorry. What am I saying? Sorry, beta is very small. I got z from this term. Sorry, z's. I guess I forgot that one. The limit of the connection form is denoted by z. Sorry. What? With sorry, the limit times r squared times connection form converge to z. So z is the leading order term of the connection form. And if you use the coordinate which has length r, then it's of order 1 over r squared. Okay, so I have this. And already immediately, this gave me one, because I know that b is of order r to the minus 3/2, and this tells us that I have a linear equation, and this determine the left hand side completely, which have the same magnitude. So this immediately tells me that this is of this the same decay rate in U. Okay. This is a divergence of a symmetric traceless 2 tensor. So determine it completely. Right. And once I know this, I can easily see that both of this limit exist, because du of is of order r to the minus 3/2 means that the derivative of c is integrable when u goes to positive and negative infinity. So for this, I just integrate the derivative. Okay, and also this is of an order which is integrable. So I know that all of this limit exists through this equation. Okay. Okay. Of course, eventually I'm interested in this quantity. So let me focus on, from now on, let me focus on this equation. I mean, the purpose of this one is to establish that this term decay at this rate so that I can define what I want. Okay? From now on, let's focus on this. So first of all, what is h? Well, h is actually very difficult to determine, but I mean, eventually I'm interested in sigma plus minus sigma minus. So, oops. Okay. Fortunately, I haven't erased the one I'm going to use immediately. So I'm interested in h, but in fact, I'm going to simply observe that it is independent of u. Then if I subtract sigma at two different values, then the contribution of h is going to go away. So then I don't need to worry about it. I can focus completely on z. Okay? For this, we look at this equation. These are of low order. So when I differentiate, I get just this part at order r to the minus 2 to s, which is, again, twice of the derivative in u. But the right-hand side, this is really, well, the least order term is what you expect when you differentiate 2 over r. So you just follow from this equation. Now you have 2 over r plus h over r squared. You're differentiating this in x. Right. Of course, you have 1 over r squared twice of the dxr plus dh dx plus no order term. It's very easy to check that the 1 over r squared term is precisely just from this part. Okay. So indeed, dh dx is equals to 0, which means that h is independent of u. Okay. So if I take the difference of sigma at any two values, subtract them, then I can cancel this part. So I only need to worry about z. Okay. So everything come down to the torsion, the connection one form, or the torsion. Okay? So what equation we have for the torsion? Well, we have the Ricci equation. Now this really determines only half of the torsion. I'm now going to use these definitions as the other half. Okay? I don't really need any of this now. After establishing these. Okay, so I have divergence of eta. This is bar minus k minus 1 over 4 trace chi bar. Curl of eta is, according to this equation, sigma 1 over 2 bar. Okay. Okay, so if I rescale this equation and take the top order term, The curl part is this. And the divergence part is this. Sorry, I should really replace this part by the Gauss equation. So I should rewrite this as mu, then it's rho minus a half multiplied by r to the minus 3 and take limit, I get divergence of z. Multiply this by r to the minus 3, I get curl of z. Okay? Now, again, I'm interested in the bar, the plus minus the minus. But what happens when I take limit as u goes to positive or negative infinity? I know, in fact, the right-hand side goes to 0. I have decay of q and these in u. So if I take limit of the right-hand side as u either goes to positive or negative infinity, I know that those are 0. So from this equation and taking limit, I know that curl of v plus equals to curl of v minus equals to 0. Okay? So in fact, if I'm only interested in the difference between positive and negative infinity of u, then the difference of z is a gradient vector field because its curl is 0. Okay? And this part would be the potential of its gradient. Okay? This part will give me the divergence part. Okay? But what is these functions? Now again, divergence integrate to 0. So I can, in fact, subtract the average of these functions from itself without changing the equation because their average value will sum up to 0. P minus its average. And of course, this part, again, doesn't matter. This part, when u goes to either positive or negative infinity, these decays in u, so that it goes to 0. This is the part that is going to be contributed to f, which was established later. Let me have a quick discussion on this part. P by itself doesn't have decays in u. For example, if you are in exactly Schwarzschild, then P is exactly n over r cubed. Okay? But since we are in asymptotically Schwarzschild, so when u goes to negative infinity, P minus P bar equals to 0, because on Schwarzschild, the P is constant over r. Rho is constant over r cubed, which means that P is constant. Now going to positive infinity to a time infinity is slightly tricky. Again, it depends on what you want. If you are in the center of mass frame for Schwarzschild, then that is 0 as well. And I think in their stability rho, well, everything converges to Minkowski, so certainly that's 0. But potentially you can have boosted Schwarzschild, and that will contribute to a non-zero P minus P bar at positive infinity. But let's say you end up in the frame with 0 velocity as well, then this term will go away as well. So at the end, we are interested in this quantity at positive and negative infinity. But that term is the leading order term of mu bar. Okay. So what I need to show is then that I need to differentiate this equation in X and show that its leading order term when differentiating in U is pointwise, this quantity. And again, if we are in bounded coordinate, this is the modified mass aspect, so this is indeed true. If you have, we already seen that this is true if we have bounded coordinate, but we can also verify this. Okay. Well, we are going to have the dx of this whole things, and I think I erased. I actually erased some of the equations I need. Let me see. Let me compute them separately. Right, the change of Gauss curvature, since my metric changed by chi bar, so the variation of Gauss curvature and around a metric which have almost constant Gauss curvature. So it's this Laplacian trace chi bar plus double divergence. Okay. I really erased most of the equations I need for the propagator equation. Let me put them back. Okay. And dx trace chi is trace chi bar trace chi k minus twice of this theta. Okay. So I see if I take the ds of the divergence, well, the metric change, but those terms are of lower order, so I can just take the divergence of this. And when I take that divergence, then this is going to cancel out with this. And then this part is going to cancel out with this part. Okay? And of course, I want to keep this term at the end, because that's the limit which goes to this. Okay. And this term is going to cancel out with this term when I differentiate this. I have a trace chi bar in front. Okay. And then this is of lower order, so it will cancel out itself. Then sure. Let's. Oops. This has to combine to lower the term. Okay. Again, they all have by itself 1 over r to the power 3, potentially. But as long as they're 1 over r to the power 3 term cancels out, is okay. Right? They cancels out, so I'm left with this term, which is what I have on the right-hand side. And again, ddx and du differ by a factor of 2. Okay. So I'm end up with this one. Okay, so okay, so if I combine all of these, I know that then let's see what I've said. Curl of z plus minus z minus is going to be 0. Divergence of plus of z minus is going to be n pointwise is f minus s bar.
We actually know both curl z plus and z minus are 0, right? Individually.
Yes, yes, yeah. But I think this part I really need this. Okay. So again, z plus minus z minus is a gradient vector field whose potential comes from f. And I guess I erased that equation. And I also know that divergence of y1 is 1/2 h plus z. This is independent of u. So if I take divergence of z minus, it's going to be z plus minus z minus. Okay, so this divergence is a gradient vector field whose potential is given by this. We combine these. Right. Okay, so this I can establish this last one, which is the sort of most important statement that the displacement is given by mass loss, and particularly it depends quadratically on the Newton's function. Even though in here we see at the instantaneous level everything depends linearly on each other. This is velocity and position, but at the end position depends on how quadratically on the velocity, or on the integral of velocity. I think this is kind of somewhat interesting. Even if you don't really care about gravitational wave experiment, we have been purely at now infinity, we are sort of treating the Newton's function, which is more or less this, sort of as a free data that we can put into our, for example, the boundary coordinate to drive the radiation. But at the end, it depends on itself, at least through integrals. There's a quadratic relation, so this should tell you that it's not so free if you consider it's sort of, if you want to, certainly if you assign it from minus infinity to positive infinity to be just something arbitrary which satisfies the decay condition, this is not going to be true, right? Its integral from minus infinity to infinity is not going to depend on itself quadratically. So at least this should tell you that although we, in a small neighborhood of the non-infinity, we are treating this as free data that we can choose to drive the radiation. Overall, when you look at the combined contribution, or if you want to assign it from spatial infinity all the way to time infinity is not so free. There are at least some constraints. And interestingly, these constraints are something you can see via a physical experiment. At least potentially one could see through a physical experiment. This gravitational wave experiment. Okay? So at the very least, from this and this part, we should see the sort of I think this is sort of the nonlinear nature of the gravitations and gravitational wave experiment that is refers to in the title of this paper. And really, at the instantaneous level, something things all depend linearly on each other, but the accumulative effect somehow depend on one linear term depend on a quadratic term of another. Okay. I think I finished. This is pretty much.
So how much are these that depend on the specific decay rate of crystal requirement? I guess the number one is this depend on the stability result.
Right, and it has to be it can be slightly lower, but it cannot be too much lower than 3/2, right? If it's -1, then it's not necessarily integrable.
It just have to be greater than 1, right?
Greater than 1, right?
Greater than 1.
Right.
And is that it, or because, for example, if I just take a boundary, just take a standard boundary size coordinate.
right.
Suppose we also know, some additional information of in terms of u dependence on u.
Right. My impression is that you really need this, at least the newer works on the stability. They have weaker assumption, but they won't allow you to do this kind of analysis. You really
Alpha, beta, which is decay rate, very different, but they don't really appear in this analysis. Alpha, beta.
right. Alpha and beta is not. Well, they have to be faster than r to the -3, I think.
Yeah, but
Right.
that's very weak.
Le-
That would be very weak assumption.
Right.
The point is called sheep.
Right. Right. So this and imagine.
But in a way, that's actually the news. So if the news actually decay, for example, the news actually decay, as in u to the minus something that is greater than 1.
Right.
Is it enough to make all the arguments work?
I think again all the. Again, if you want. Again, for example, there's a p minus p bar term, and if you don't assume, for example, asymptotic is Schwarzschild,
Yeah.
then, that term would probably have contributions.
But that decay, yeah, but the decay is the same, right? That's R to the -3, that's actually rho.
Right, but
The decay is the same, but you have to assume it's stable.
I think this, right,
This has
rho,
nothing to do with the decay rate.
right, rho has a decay,
But this is standard.
Right, this is standard.
Standard decay rate, but you
Right.
just have to assume that special infinity and
I need to know the rescale limit, what it does at spatial and now infinity.
right.
I mean, assuming that, I can add a term to the result. I think some of the, for example, Lydia's result does include this term.
It's rho.
the contribution from rho, which is I think in terms of p, assuming you have. But I think that's just when your final friend is not the center of mass friend, then certainly you get one more term from p plus. Right. But I think in principle, if you start with something that is not homogeneous in 1 over r, you probably also get one more term from p minus. Right. So if you assume you know not just have O 1 over r, but you know what is the 1 over r term, you can probably compute p minus, and then add that term to the gradient, to the potential on the right hand side. I mean, right, certainly, if you're this doesn't have to be 0, as long as your asymptotic allow you to anchor these terms, then it's straightforward to add them into the equation.
For every u, there are cannot we know that in the beginning and in the end,
Right.
But is this also the case for every u?
Well, again, you are taking the difference between initial and final, so you don't really need the yes.
You have this big hierarchy of data and make some assumption about how they behave.
Right.
For large R and for U.
Right.
And you have these quantities like U and like the shear.
Right.
So is there any way of you try to write down a Monty's X coordinate system for these things, assuming like your U is your mass aspect and your
Right. I think in that case, right. I think.
you have good guesses that you could build out of the stuff that you got, and then you just try to write down a coordinate system and show them this stuff.
Right. I think in bounded coordinates, for example, the shears are either the shears they are CAB, du of CAB, and alpha bar will be second derivative of CAB. And it's proportional. So in the bounded coordinate, this you can just write it down each of the component and just verify. And in bounded coordinate, this will be the modified mass aspect. I think the double divergence from here will cancel out those from K. And this is H square. So
So it's really
So-
additional assumptions on the U, I mean, on the U dependence, and on
Right,
the
right.
work.
right. And I think some of the, if you have weaker assumption at the beginning, you may not have decay rate of the vial curvature. I think in some of the, if you start with something that's fairly much weaker than crystalline Kahneman, then you don't even necessarily have any decay rate of the vial curvature, at least, or much weaker decay rate. And I'm not sure H, but that's probably easy to figure out to write H in the bounded coordinate.
Is there any notion of angular momentum memory by using zeta or something like this?
Well, this is the top order term. You have to go one more order into Z, right? This is the leading order term of zeta, which is one order higher than you need. Right. Well, you have this and you have this. So I'm not sure which one would be more useful to you. You have propagator equation for this, and as well as the Ricci equation. Both could be related to what you need, but I'm not sure which one. Again, you have to go down one more order, so since it would be tricky, but both potentially would be useful, I think.